Welcome to the last module of this entire course. In this module, Module 7, I will be putting all of the pieces that we have developed together into one neat, unified package. And what we're going to have to do in this module is connect the robotics piece that we discussed early on, differential drive, mobile robots, odometry, sensors, to the control theoretic developments that we've gone through. And in particular, we need to see how we can take the navigation algorithms we have developed and actually make them fit onto the actual robotic platforms that we're interested in. And the first lecture is really going to be a little bit of a high-level discussions of what are the things that we need to be aware of when we start putting things together. I've called it approximations and abstractions. And the reason for that is whenever we try to design control systems or navigation algorithms, we're using models. And we need to understand when these models are indeed relevant or useful or applicable. So recall our rather messy yet exciting hybrid automaton. When we developed this, we assumed that we had perfect sensing. We even assumed that x dot was equal to u, meaning that we directly could control the velocities of the robot. But then, as we saw at the end of the last module, we ran it on a differential drive mobile robot. And these two robot or systems, the actual differential drive mobile robot and x dot equal to u, it's very unclear what they even have in common. How do we make our models fit the reality? Or more importantly, when are the models relevant to the real world? Well, I like to think of models as fables. Let's return to our old friend, the hare and the tortoise. So when we discussed the Zeno phenomenon, we had the hare race a tortoise. Well, I don't exactly know where all of you live, but chances are that where you live, very rarely do you see hares and tortoises actually racing. So here is a story or a fable that never applies. But somehow we still gain some kind of insight into the real world from this story. Like slow and steady wins the race if the tortoise wins, or in the Zeno case, the hare is going to win. Well, what we should take away from that is, well, don't rush it when you're doing the quizzes for this course. Right, so now the hare and the tortoise actually had something to say about how we should approach the course. And similarly, the models are fables. They have some relevance, but they're not exactly telling the full story. So let's take a step back and see what assumptions did we actually make. And what kind of models did we actually use when we were talking about the robots? Well, we really had two main classes of assumptions. One was the dynamics. And when we developed our control algorithms, we made the assumption that we had this particle located at x, where we immediately controlled the velocity. X dot is equal to u. Well, that may or may not be reasonable. We also made this assumption that the robot has a sensor suite. It's actually one of these sensor skirts that allows the robot to see roughly a disk around it. That's not exactly true, because as we saw in the last module, we only see certain parts of this disk. But from an assumption point of view, we still kind of made the assumption that we can see everything around us up to a point, and we can measure where obstacles are and the angle to that obstacle. Well, it turns out that the sensing assumption is more or less okay. As the robot moves around, you can actually build up rather accurate models or maps of what's going on in the world. The problem is with the dynamics. This is not even close to being reasonable. The Capera 3 that we've used a lot, it's not at all looking like x dot is equal to u. So in order for our fable, or our model, or our navigation algorithm to be relevant to the actual robot, we somehow need to remedy this lack of reasonability. So the problem, of course, is that we have the point mass, and then we're using a unicycle model for actually describing the robot, where x dot is v cosine phi, where v is the speed, and phi is the heading. Y dot was v sine phi, and phi dot was equal to omega, where omega was the angular velocity. Well, this robot, or this model, doesn't act like x dot is equal to u. And somehow, for what we've done during the last couple of modules, to be relevant, we need to make these two models actually coexist peacefully. So what we're going to spend the next few lectures on is a very, very simple problem, which is how do we make a unicycle robot or a differential drive mobile robot act like x dot is equal to u?